Welcome to the first video in the Intermediate Algebra series. We're going to start with a little bit of review. And so the first topic we're going to talk about today is set notation. So this gives us a chance to describe a set of numbers. There's three methods you can use. We have the listing method. Anytime we describe a set of numbers, we usually use a capital letter to represent the name of that set. So, for example, we could use a capital A to represent the set of the numbers 1, 2, and 3. With the listing method, we literally just make a list of the numbers that are in the set, and we use the curly Q brackets around our list. So if we were to draw a picture of set A on a number line, we really just have three, usually they're called elements, right? The number 1, the number 2, and the number 3. So the listing method works really well. Usually if you have either a small amount of elements or a small amount of numbers, so that you can list them out, or maybe you have a larger list that follows a pattern so that you could kind of indicate the pattern. You could use the listing method for that. Sometimes we have a set of numbers that includes too many elements to list out. So in that case, we would need to use something else. We have two options. We have the set builder notation and the interval notation. So let's say, for example, that we wanted to represent the set of numbers between 1 and 3. So that would include 1, and then everything between 1 and 2. It would include 2, all the way up to 3. Right? Obviously, I can't list all these numbers out. There are too many numbers between 1 and 2 to make a list. So these would be things like 1.5, 1.2, 1.01, 1.001, right? There's too many in here. We could use fractions, decimals, all kinds of things. There's too many to list. So let's call this set B. We use something called set builder notation, where we choose a variable to represent any of the numbers in this set. I'll just use X because that's the most common. So we're going to write set B as the set of all X such that, and then we're going to list a criteria so that X will have to lie in this range. So I want X values that are greater than or equal to 1, and X values that are less than or equal to 3. And if I use the word and, I mean that I have to satisfy both at the same time. So any number that is at the same time greater than or equal to 1 and less than or equal to 3. And that will encompass all of these numbers here. So this usually reads, right, just like we read it just now, the set, that's not going to work, the set of all X, and then this is the such that okay, and then we have our criteria right here that describes what numbers are going to be included. Okay, just as a side note, right, I could have combined these two inequalities into one. And so you could write it as a double inequality. Because we're talking about numbers in between 1 and 3, we could have written it like this as well. Right? We can write it either way, it doesn't matter. If I had two separate shaded regions, I wouldn't be able to write it together. But since I just have one, I can do that. Okay, so that's called set builder notation. The other option when we cannot make a list of the numbers is called interval notation. And this is sort of a shortcut method. where we list the endpoints from left to right, separated by a comma. So there's also some brackets that we'll use. So let me jot down that information first. So if I use the square brackets, that's going to indicate that the endpoint is included. But if I use a round parentheses, that's going to indicate that the endpoint is not included. In this particular example, I'm just going to write this same set B, right? I am including the 1, which would be the end of this shaded region, so it's the endpoint on the left, and I am including the 3, so I'm going to use the square bracket. And I list the endpoints from left to right, so I'm basically saying all the numbers from 1 up to 3, including 1 and including 3. We'll take more time to talk about interval notation as time goes on. That's definitely something that is going to come up a lot in college algebra. It's not a bad idea to start thinking towards that now. But at the moment, you can use these two interchangeably, if you like. Okay, also in this section, we're going to just review some of the different types of numbers, and this will give us a chance to practice all those methods we just talked about. So we'll start with the natural numbers. These are the counting numbers, and there's a pattern to them. So we could use the listing method, say 1, 2, 3, and we're going to continue with that pattern, so we can use the ellipsis, the dot, 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 to continue that list on forever. For whole numbers, we're going to add the 0. Same thing's true, we've established a pattern, so we can use the ellipsis. For integers, these are positive and negative whole numbers. So now our pattern actually goes in 2 directions. We have some negative numbers, 0, and then positive numbers, and again, we have a pattern. Okay, once we get to the rational numbers, we can't really list them out anymore. So remember what rational numbers are. These are numbers that can be written as a fraction. Fractions can also look like terminating or repeating decimals, or all of these sets actually are getting bigger. So the natural numbers are contained in the whole numbers, which are contained in the integers, which are contained in the rational numbers. So some examples of rational numbers would be like 1/2 is a fraction, right? 0.333 repeating would be the same as a fraction of 1/3, okay? Any terminating decimals like 2.5, right? Anything like that. All of those, or just regular integers like 5. All of those would be rational numbers. We usually use the set builder notation for this. So because they can be written as a fraction, we say that Q represents the set of rational numbers. P over Q, it's a fraction, such that P and Q are integers. Now, I would never ask you to come up with this on a test, okay? This one's a little bit more complicated than the one we did earlier, but it follows the same method. So this is just kind of a demonstration of that. Okay, beyond the rational numbers, which can be written as fractions, sort of as a separate set, we have the set of irrational numbers that cannot be written as fractions. So these would be non-terminating or non-repeating decimals. Pi is a really good example of this, right? That's that number that goes on forever and ever, and it doesn't repeat and it doesn't stop. So that's definitely in this set. A lot of the square roots, like square root of 2 or square root of 5, also non-repeating decimals, right, that don't come to an end. Okay, if I take these two sets together, they're definitely separate. You can tell by their definitions, but if I put them together in one big set, I get the set of real numbers. And all that we're going to be working with for the majority of the class is real numbers. So you'll see that come up a lot. Outside of the real numbers are a set of complex numbers, which we'll get to very late in the course. And this involves the square root of a negative number. So we use, it's called the imaginary unit to represent the square root of -1. We're not there yet, but we will get there. Okay, we're just kind of running through some of the topics in the first couple sections of the chapter book. The next topic is properties of real numbers. So there are properties for both addition and multiplication. And I'm going to kind of assume that you've seen these in the past, so I'm not going to take a lot of time to delve into these. Maybe I'll add an additional video if you're interested in learning more about these. We're going to be using these regularly, but we're probably not going to talk about it. So it is kind of important that you know that they exist. The one that we're going to talk about the most is the distributive property, this last one. The distributive property is the one that says I can multiply over either addition or subtraction and distribute a number out front of a parentheses. So I brought a couple examples here to try this out. Usually you've done this before, but it's a good just to take a revisit in case it's been a while. So I can use the distributive property here, right? 5x multiplied by 2x would give me 10x squared. And then 5x multiplied by 3 would give me 15x. Okay, the second one, I always like to include something like this because it looks a little bit confusing. There's an implied 1 here right in front of the parentheses, right there. So when I do the distributive property, I am not distributing the 10. I'm only distributing the negative or a -1. So this is one of those that I usually put on the test just to make sure that you've picked up on that. It is kind of important. So the 10 initially is just hanging out in the front. -1 times 1 would be -1. -1 times a would be -1a or -a. You can write it either way. And then to make it as simple as possible, we can combine the two real numbers here. So 10 minus 1 would be 9 minus 1a. Or 9 minus a would be fine as well. Okay, same thing's true for this last example. We're not, please, please, please don't subtract these. That always makes me cry a little. It's the -2 that we're distributing. So again, the 3 is going to kind of hang out for a minute in the front. This will be a -10 plus 10x minus 2x squared. Then we're able to combine these numbers together at the bottom here. And it's usually a good idea to write it in descending powers of your variable. So the highest exponent is the squared, and any negative is attached to the number behind it. So this would be the same as -2x squared plus 10x, and these two added together would be a -7. couple more quick topics in the next section. They're gonna introduce the idea of a number line. I don't think that's a foreign topic to you, right? 0 is usually in the middle, and we're gonna count positive numbers on the right, negative numbers on the left. These kind of go together, so that sets us up for the idea of absolute value. So absolute value are the two bars around a number, and it indicates that we're talking about just the number's distance from 0. Because we're talking about a distance, it's always going to be equal to a positive number, right? So 2, for example, on the number line, 2 is 2 jumps away from 0, so its distance from 0 would be 2. Right? Negative 3.5 would be somewhere over here, and again I could do the jumps, but it's 3.5 jumps away from 0, and so the absolute value makes it positive. Eventually we're going to solve equations like this. So if I have a number whose absolute value is 5, there's really 2 possibilities, right? I could be 5 jumps away on the right. 1, 2, 3, 4, 5. So x could be positive 5. Because if I were to plug that in, the absolute value of 5 is 5, right? Or 1, 2, 3, 4, 5. I could be 5 jumps away on the left, and x could be negative 5. The absolute value of a negative 5 inside here would also give me 5. So I get 2 solutions. And we'll take some time to go over that in detail later on in the course. Okay, we have what's called the additive inverse. Sometimes this is combined with those properties that we were just talking about. And that just means that really it's the opposite, right? So if I have a number, it's going to be its negative is the additive inverse. The opposite, or the additive inverse of pi, would be negative pi. And the opposite of something negative would be something positive. So the opposite of negative 3/4 would be positive 3/4. The opposite of 6x minus 2, I have to make both parts opposite, so I'm kind of distributing a negative. So the 6x would be negative, and the 2 would be positive, so that if I were to add these two together, I would get 0. All right, there's lots more in this chapter. There's a little bit about how to operate with positive and negative numbers. If that's something you feel like you need to review, you can do that. And I may include an extra video for you if you're interested in looking at that. I did think it might be worthwhile just to give you a quick fraction review, nothing in depth. So I'll do that, and then we'll end this video and kind of consider this a good bit of review. Okay, so adding and subtracting, remember we have to have a common denominator to do that. So the denominator is telling us what kind of fractions we're adding or subtracting. Here we're adding or subtracting, I guess, halves. So I have 5 halves minus negative 3 halves. First of all, when I subtract a negative, that's really the same as 5 halves plus 3 halves. I keep the denominator, right? And I add the numerators. And if I can, I should reduce if it's possible. For the second example here, I don't have the same denominator, so I would like to get the same denominator. This is that least common multiple idea, right? So the smallest number that 6 and 4 both divide into would be what? 12, right? So to get to 12, I need to multiply the 6 by 2. And anything I do to the bottom, I have to do to the top. To get to 12 on the bottom, on this side, I'd have to multiply the 4 by 3, which means I have to multiply the top by 3 as well. So this is going to give us 2 over 12 plus 3 over 12. Now the denominators are the same, so they match. Right? I'm not adding apples and oranges anymore. Oh, there's a negative in here. Okay, so negative 2 plus 3 would be positive 1/12. For multiplying, keep in mind that any whole number can be represented as a fraction. So 8 would be the same as 8 over 1. Okay. You can do your simplifying at the beginning or at the end. So you could multiply these together first and then take out any common factors. Or you could say, hey, 2 goes into 8, so I can go ahead and divide both of these by 2 and then multiply across. Negative 5 times 4 is negative 20, and 1 times 1 is 1. So I multiply both the tops and the bottoms. Last is dividing. So I usually do the keep, change, flip, right? So keep the first, change it to multiplying, flip the second. So again, I'm going to write this as a fraction, so negative 10 over 1. I'm keeping that the same. I'm just making a fraction so it matches up. Change this to multiplying and flip this one over. So it doesn't matter where you put the negative. I'm going to keep it with the 5. How about that? Okay, you can do it either way. You could cancel out your negative 5 here, or you could multiply it first and then cancel it out. If I divide both of these by negative 5, this is going to give me a 2. It's going to cancel and give me a 1. 2 times 6 is 12. 1 times 1 is 1. All right, I hope that gave you a quick review. If you need more information on any of these topics, I'd be happy to refer you to other videos or resources and things like that. So just keep me posted. Good luck. We'll see you in the next one.